In this video, we're going to review the solutions to the harmonic oscillator approximation that describes or approximates molecular bond vibration. So we set up the problem in the same way as we set up the problem for the particle in the box. You'll note a couple changes. The first one is that we use this mu, this reduced mass, and that makes more sense in our bond where we have two moving masses to describe them with a reduced mass rather than the moving masses of each two components. The second difference between this and the particle in the box is that we actually have a potential energy. So our potential energy isn't zero or infinity when you're inside or outside the box, but it depends on the bond vibration or in the bond length. So the potential energy, we treat our molecule as a spring, and the potential energy is 1/2 kx squared. So we can take that and substitute that in for our potential energy, and that's going to give us our differential equation that we need to solve. Okay, so now we have our differential equation, and we need to figure out how to solve it. So we're not actually going to figure out how to solve this problem. This is a solution that's known. This isn't a math class, it's a chemistry class, so we don't care too much about how to solve a lot of these differential equations, just to know when they can and when they can't be solved. So the solutions to this differential equation depend on one quantum number, n, as we have a two-dimensional problem. And they take the form a sub n, h sub n as a function of alpha to the 1/2 times x, and then times e to the minus alpha x squared over 2. Okay, so what are these various terms? We have three different terms in these wave functions. The first of which is just this simply e to the minus alpha x squared over 2. That's a function, we all know what that is. The other two terms we have are a sub n, and this is a normalization constant. So this is a constant that depends on the quantum number n. It's equal to 1 over the square root of 2 to the n times n factorial, and then multiplied by alpha over pi to the 1/4. You can see alpha is appearing in all of these terms. Alpha is a pooling of our various constants. So alpha is the square root of k mu divided by h bar. Okay, so our a term is a constant. Our h term is not a constant. So h sub n are the Hermite polynomials. So this is a polynomial series that takes the form minus 1 to the n times e to the minus alpha, e to the minus x squared, sorry, or e to the x squared over 2, rather. And then we multiply that by the n derivatives of e to the minus x squared over 2. That's why I'm getting my minus confused. So you can see that this term here is a way to generate polynomials. And when we do that, we get a variety of polynomials. So for example, our h0 is a function of x is equal to 1. h1 is a function of x is equal to 2x. h2 as a function of x is equal to 4x squared minus 2, and so on. Now, our Hermite polynomials in our eigenfunction solutions are not functions of x. They are functions of the square root of alpha times x. So to generate them, all we have to do is put in an alpha square root of alpha times x every time we see an x in our Hermite polynomials. So our h0 is still 1. Our h1 as a function of alpha to 1/2 times x is now equal to 2 alpha 1/2 times x. Our h2 as a function of alpha 1/2 times x is equal to 4 alpha x squared minus 2, and so on. So be sure you do that. That term there in our wave function solutions is not times the square root of alpha times x, but it's showing that our Hermite polynomials are functions of the square root of alpha times x. Okay, so we can put all of these together to come up with the wave function solutions. So let's look at the first couple for that. So our ground state, our size 0 as a function of x is going to equal to a0, h0 as a function of alpha 1/2 times x, and then e to the minus alpha x squared over 2. So a0, if n is equal to 0, then our 2 to the n is 1, and n factorial is 1. So a to the 0, or a0 is simply alpha pi over pi to the 1/4. Our 0th order Hermite polynomial is just 1, and then we have e to the minus alpha x squared over 2. So our total wave function, eigenfunction solution here is alpha over pi to the 1/4 times e to the minus alpha x squared over 2. We look at the first one as well, the first excited state, psi1. Again, it's just going to be a1 h1 time of the plus a function of alpha to the 1/2 x, and then e to the minus alpha x squared over 2. So in the case of a1, now our normalization constant is 1 over the square root of 2 times alpha over pi to the 1/4. Our first order Harmonic polynomial is 2 times the square root of alpha times x, and then we have e to the minus alpha x squared over 2. So pooling all of the constants, we end up with 4 alpha cubed over pi to the 1/4, and then times x e to the minus alpha x squared over 2 as our first solution, our first excited state solution. All right, so from here, we have the wave functions, and we could calculate many more wave functions if we wanted, many more eigenfunction solutions. But what we're ultimately interested more often than not is the energy. So to solve the energy, we take our wave functions, we put them back into the Schrodinger equation, and we find this constant that they come out. They should be again multiplied by their same wave function. So to start, we can take 2 derivatives of our ground state. We could do it for any state, and we'll see how the energy changes as a function of quantum number n. I'll just provide that for you at the end. But if we can evaluate the ground state, so we'll need to take 2 derivatives of the ground state. So the first derivative of our ground state here is going to be as follows. So our constants up front are alpha over pi to the 1/4, that remains unchanged. And then we'll need to take the derivative of that Gaussian term on the inside. And we can do that, and we need to use the chain rule. So we'll take that term, so e to the minus alpha x squared over 2, and then we'll multiply it by the derivative of what's in the exponent, which in this case is minus alpha x. And then we'll take the second derivative. So the second derivative of our psi naught is just going to be derivative of this function up here. Again, our constant term is unaffected by the derivative, and now we'll use the product rule in addition to the chain rule. So we'll multiply this by e to the minus alpha x squared over 2 times minus alpha, and then we'll add minus alpha x, and then times the derivative of this, which is minus e to the minus alpha x squared over 2 times minus alpha x again. Okay. So now I'm going to see that we can factor out e to the minus alpha x squared over 2 from both parts of the equation, and that will give us our original wave function. So here I'll write this as alpha over pi to the 1/4 times e to the minus alpha x squared over 2. And you can see now that this is our original function psi naught, which is exactly what we want to see. And then what's left over in here? Well, we have a alpha squared x squared term coming from right here. And then from this first term, we have minus alpha. So we can ultimately write this as alpha squared x squared minus alpha times psi naught as a function of x after we've taken 2 derivatives. All right, now we can take this, plug it back into the Schrodinger equation. So our Schrodinger equation is going to be negative h bar squared over 2 mu times the second derivative with respect to x of our wave function, which we've already solved for here. So that is alpha squared x squared minus alpha times our wave function. Then we have plus 1/2 kx squared times our wave function. And this is supposed to equal some constant, that's our energy, times our wave function again. You can see in all 3 of these terms, we have our wave function, so that cancels out, which means we're a good ways away, or a good step closer to getting the actual constant that we want. All right, so what we have here is minus h bar squared, alpha squared, x squared over 2 mu, and then plus h bar squared alpha over 2 mu, plus 1/2 kx squared is equal to e. So right now, it might not be obvious how we're supposed to get rid of x, because we need to get rid of x in order to get a constant. But remember that alpha is our pooling of various variables. So we can go up here and look at what alpha is. And alpha is the square root of k mu over h bar. So we can plug in what alpha is into our equation and see if that helps us. All right, so in this first term, we'll have minus h bar squared x squared over 2 mu, and then we'll have an alpha squared. And remember, alpha is the square root of k mu over h bar. So alpha squared is going to be k mu over h bar squared. And then we'll have h bar squared over 2 mu times the square root of k mu over h bar. And then we have plus 1/2 kx squared. So you can see here in this first term, we're going to cancel out our h bar, we're going to cancel out our mu, and what we're left with is actually minus 1/2 kx squared, which is exactly cancels this potential term here. So that removes the x dependence, and we just have an energy that's equal to h times the square root of k mu over 2 mu, and I'm going to rewrite that as h bar over 2 times the square root of k over mu. And this is our energy for the ground state. You can see it's not zero, just like we see for the particle in the box. In general, we could carry this on for many different calculations, and we'd have our E sub n, so energy as a function of n, is equal to h bar times the square root of k over mu. And that is how this depends on the quantum number n, is n plus 1/2 is here. So you can see for our ground state, n equals 0, and we get h bar over 2 times the square root of k over mu, which is exactly what we got when we evaluated the Schrodinger equation. You'll also commonly see this in spectroscopy written as hc nu, and then times n plus 1/2. So what's going on here is we're re-expressing our h bar times the square root of k over mu, and we're pooling those constants into this new term. And this new term comes in inverse centimeters, so to compensate, your speed of light also needs to be in centimeters. And this is what's probably more often looked up if you're trying to find these values. It's easier to express that nu rather than the bond, the force constant of the bond and the reduced mass, but it's based on both of those. So this, in summary, this review has shown how we can solve for the eigenfunctions and the total energy of the quantum mechanical harmonic oscillator.